Hello everyone, I'm Himanshu Tripathi, Assistant Professor from Electronics and Communication Engineering Department at Akgec Engineering College. And in today's session, we will see that how to control the GPIO operations with ESP32 microcontroller. In previous session, I have shown you that how to control the GPIOs. Specifically, we have controlled the LED that is presented on board on this ESP32 microcontroller. And in last session, we also discussed about the problem related with this time dot sleep. So this time dot sleep is a blocking delay. Let's define here. This is the blocking delay, and we need to avoid this blocking delay at any cost, because if we are interested in multitasking in IoT, definitely we need to do multitasking. We need to get values from different sensors at different time intervals, and at the same time we need to be sure that how to when to connect with the internet, when to push data into the network or to the cloud, and these may be the various functions that we are intending to perform with our microcontroller unit. So here our microcontroller unit is ESP32, and we will see that how we can use non-blocking time delays in our next step. So I have opened a new window here, new editor window here in Thorny IDE, and here in this script I am using non-blocking delay for LED blinking. So quickly we will see that how we can use non-blocking delay. For this, I am importing few modules: import machine and import time, right? So if we are really interested in non-blocking delays, there may be two possible options, or maybe three possible options. Let me introduce you about these three possible options. The first option is we can use time underscore ticks method that is available inside this time module. This is a timer that is active on your every microcontroller, whether it may be Arduino, it may be ESP32, or it may be any other microcontroller. In Arduino, we generally call this timer as millis, but in MicroPython based implementation, we call this time underscore ticks. So what this millis or what this time underscore ticks is actually, it is a watch. Whenever we power up this microcontroller, this timer automatically starts, and it is keeping the track of time in milliseconds. For example, if I have just powered up this microcontroller, and if I am reading that what is the value of time underscore ticks, it will return me the milliseconds that have been passed, that we have used this, we have powered up this microcontroller. Let's quickly see whether this thing is working or not. So let's say t is equal to time underscore ticks, time dot ticks underscore ms. So this time dot ticks underscore ms will return the value, that is the milliseconds that have been passed since we have powered up this microcontroller. Let's print this and see what is happening. So here you have seen the value 2040605. These much milliseconds have been passed. So again, if I am running this script, this value has been incremented. Continuously, this timer is working with this microcontroller. So this may be one implementation of non-blocking delays if we are using this ticks underscore ms function that is available inside the time module. Another way of producing non-blocking delay is the implementation of hardware timers. In ESP32, there are 4 hardware timers: 0, 1, 2, and 3 are the names of these hardware timers. And we can configure any hardware timer so that we can time the events that we want to implement or we want to execute on this microcontroller. And the third method that is nowadays very popular is using the async IO module. While we are using async IO module, the multitasking is becoming pretty easier, but it comes with their own syntax and their own way of working. For any module, we will be using some timers based operations. So today we will see that how to use ticks_ms for producing non-blocking delays. So for that purpose, let me delete these two lines and create one object for LED machine.pin. Then the pin of that LED, I know that my LED is connected at pin number 2. Then machine.pin.out. Now this pin number 2 is being configured as output pin. Pin 2, that is the GPIO pin. GPIO is an output pin, right? So after doing this, what we can do, we can simply write some program, write some script. So here I'm trying something, and inside this I'm using the indefinite loop while true, and inside this what I am doing, I am basically reading the current time. So current time is equal to time dot ticks_ms. So if I have read that current time here, then I will do if the difference between time dot ticks_ms minus current time is greater than the blink interval. So I have used here current time and blink interval. These are the two variables, and let's define these two variables. Current time is equal to 0 and the blink interval is equal to, let's say, 500 milliseconds. Okay, and one more variable I may be requiring here, that is the last time when LED was toggled or the state of LED was changed, and let's say it is 0, right? These were the initializations of variables, right? Then if this condition happens, like the present time minus the current time, that difference is sorry, here should be the last time, and let me remove this line as well. If the difference between the current time is nothing but the time dot ticks_ms. Earlier I was using the current time, but I thought that this will be more easy and with less typing. So the current time is time dot ticks_ms minus the last time we toggled the state of LED, and for the first instance the last time was 0, and if that difference is greater than the blink interval is 500 milliseconds that I have defined, then I need to toggle the state of LED, and for toggling the state of LED I can write LED dot value, then not LED dot value. The status of LED has been toggled, and let's print the status here on REPL. LED is on if LED dot value, else I will print LED is off, right? Then what I need to do, I need to change the last time. I need to keep record of that last time, that is equal to time dot ticks_ms, right? And we will finish that if statement with this thing, right? And what about stopping this script? Except keyboard interrupt and here I can write print script stopped using keyboard interrupt, that is the control plus C, right? And if we are interested in clean exit, I can write LED dot off, so that it doesn't matter at whatever instance we are pressing control C, whenever we are stopping this script, our LED is going to remain off. So this is the thing, current time is no longer required. Let me remove from this, and two variables I am using, blink interval and the last time. We are comparing the last toggle time with the present time, and if that difference is greater than blink interval, we can change the LED value. Let's see that how this script is behaving. Now you can see that our LED is blinking continuously, right? So this is the very basic implementation of non-blocking delay. And let me stop this script. Okay, now the script is stopped and you can see that our LED is off. So this is the clean exit from the GPIOs. One more thing, here you might ask me a question that how we can prove that this delay is not blocking the operation or the execution of a script at the microcontroller. So what if I am using another if statement, and again I am time dot ticks underscore ms minus last print time, this is another variable that I am using, is greater than print interval, right? So we have used two new variables here, last print time and the print interval. Let's define these two variables. Last print time is equal to 0 and print interval, let's say after every 3 seconds, sorry, 3000, these are in milliseconds. Okay, now what we are going to do, we are going to implement two different tasks. First task is basically for LED blinking. So here I am continuously blinking or toggling the state of LED, right, by using this first if block, and the second if block will handle some statement printing, right? So if that is happening, print some statement, another task, let's say this is the statement in our script, and update the last print time. Last print time is equal to time dot ticks underscore ms, right? So this is the implementation of two tasks at a time, and this will show you that no task is blocking another task. Every task will execute whenever the time comes. So let's try to run this script, and you can see that after every 3 seconds I'll be printing one message, that is another task, right? 1 2 3 4 5 6, that is one LED blinking is going to take 500 milliseconds. After 6 print statement, we are having this statement, that is another task. So both the tasks are running smoothly on this microcontroller device. So this gives me an idea that we can basically execute different tasks without blocking the execution of the code in the microcontroller. So let's quickly refine this code in a more interesting way, and we will try to write this code so that we can easily convert this code into the class in future application. So let's say that we are not blinking the LED. The on time of the LED is different and the off time of the LED is different. Let's say that for 500 millisecond, I want my LED to be turned off, and for let's say 2 seconds, I want my LED to remain turned on situation, right? So if we need to write that code, how to write that kind of a script using MicroPython. So if we are using the same thing here, or we can use a new file, and we will call this LED toggling. That means different on and off time using non-blocking delay, right? For that purpose, I'm importing few modules, import machine and import time. And let's quickly create an object for the LED. That is, LED is equal to machine dot pin, and the pin that with which LED is connected is pin number 2 in our case. Then machine dot pin dot out, right? So we have configured our LED into the output mode. LED pin is basically being configured as an output mode. And let's try to write some code. Try, then while true, and inside this what we are doing, let's say current time is equal to time dot text underscore ms. This will read the current time, and if time, sorry, if current time minus last time is greater than on time, let's say, and let's put this thing in one bracket so that it will be clear when we see. And let's say LED state is equal to double equal, that means we are comparing that LED state. So here what we are doing, current time minus last time is greater than on time, right? On time has been passed and LED state is 1, that means LED is still on. Then we can do something. Let's separate this thing as well so that it will be clear. We are using two conditions for this if. The first condition that should hold true, that is the current time and last time difference should be greater than on time. And the second condition that should be true, that is LED state is equal to 1. That means it's time to turn off that LED. How to turn off that LED? We will LED state is equal to not LED state, okay, and we will pass this value LED dot value. Inside this I will pass this LED state. There are too many variables. Let's quickly define these variables as well. Current time is equal to 0, and initial value of that current time is 0. Then the second variable is last time when we did that operation is equal to 0. Initially it was 0, and then LED state is equal to 0. Default LED state is 0 from here. Then LED dot value is LED state, and print this thing, print LED is off, because we are turning off this LED, right? Then the second condition is if, one more thing we need to do here, we need to update the last time. Last time is equal to current time. Great. Then the second condition is if, same kind of condition is here, current time minus last time is greater than off time, and LED state is equal to 0. Then we will do the same operation. LED state is equal to not LED state. In place of this, we need to define LED state clearly. LED state is equal to 0, and here we can define this thing. LED state is equal to 1, and then LED dot value, and inside this we will pass the LED state. And the next thing is we need to use a print statement for debugging purpose. Print and write LED is on and update the last time is equal to current time. Okay. So this is complete, and complete this script, except keyboard interrupt, then print script stop using Control plus C, and let's say that LED is off for clean exit purpose. So this is the script, and let's see whether this script is going to work or not. I'm getting invalid syntax at line number 15. Why this is happening? Last time an LED state is equal to 1, and let's solve this. On time is not defined. Okay, these two variables remain unchanged. On time is, let's say, for 500, and off time, let's say, for 800. Okay, now again run this script, and LED is on off, on off, on off, on off. Here you can see that this LED is perfectly toggling its state. If I am changing these values to, let's say, for 3000, let's see what is happening. First we need to stop the script using Control C, and again we are running this script. So now this is happening. On your screen you can see that let me show you that LED is off for 3 seconds and on for 500 milliseconds. So these values are in milliseconds. So this is the way how we can control multiple tasks using the non-blocking delay operations that I have shown you. If you are interested, this basically draws your interest into a very interesting concept in embedded system programming, that is the time machine concept, state variables and the state machine concept. And if we talk about the state variables, these may become your state variables, and this is the machine that is basically using these state variables in controlling the LED. So if we are interested, we can convert this code into a class, and if we are making a class, that means we can handle multiple LEDs, and all those LEDs can be on and off at multiple or different time intervals. So this is the very interesting approach when we are interested in multitasking with our ESP32 microcontroller. And in case of IoT, it is always recommended that please don't use the time blocking delays. Blocking delays basically blocks the execution of the code for a certain period of time, and in that case you cannot do multitasking efficiently. If you are trying to do multitasking, then please use the non-blocking delays. This is the one operation. Another implementation of non-blocking delays may be with timers or hardware timers. So this is all for this session. Thank you very much.